British style timekeeping and not Greek style. So next speaker is Rutten.
Sorry about that. Dear Prakash, it's a great pleasure to be here and to give a talk on the occasion of your 60th birthday.
Please don't describe it as we did in Amsterdam.
More. This will not be a technical talk, at least for the first 5 minutes. And then the rest will be elementary, so don't worry too much. This is what I want to talk about. Die schöne Schmetterling, de mooie vlinder, la bella mariposa, and then all these other words from different languages. They all mean the same thing. Probably it's clear what it means, at least for some of us. If your language is on the slide, it means the beautiful butterfly. So all these words are denoting the same concept, butterfly. So it's incredible that there are that many different. This is kind of related, but all the other stuff is kind of very different. And the butterfly is in this story, this butterfly. We've seen maybe more beautiful butterflies, but this is this is how we call it at some stage. And this is very much our joint work. And in order to, this will be the topic of the talk. I will say more about that in a second. But first, I want to position it in the history of our friendship, which is briefly summarized here. Let me point out that in mathematics you give 3 dots to indicate that this can go on forever. Now I've used 6 dots, so you don't miss the point. I hope that this will still continue forever. So it's definitely not finished. It started in Tampere, and this is not the place, neither is there the time to tell all the stories about that beginning. There was lots of sunshine, almost day and night, and we met in a discotheque essentially. Let's keep it at that. And then at the background there was ICAL. And then there was it definitely distracted us, yes. Then there were many more meetings, both in Europe and in Canada, and later on as well. I just want to briefly mention a few other ones. In particular, you organized this workshop in Montreal in 2002 about concurrency and probabilistic systems, where you also gave ample space for 4 hours run, which I appreciate very much. Then in 2006 there was a dramatic event at CWI, at least for some of us, including Frank de Boer, who was here, and Farad Arbab and myself. We had a dramatically bad evaluation of our group. We ended up lowest of the institute, and that was the reason for the management to re-evaluate us. So we got a re-evaluation committee, and we were free to suggest names. And then what is the definition of a friend? Well, a friend is probably somebody who, if you are in trouble and you ask for help, such a person provides help. Now that's exactly what we did. We proposed you for this committee. You were accepted by the management as one of the members, and you saved our asses. All 3 of us. And we are still being in a kind of reasonable good position because of that historic event. So that's one of the other things I'm extremely grateful for. Apart from all the other obvious things which I'm not going to name, like inspiration and examples and mathematical interaction. This is then about this butterfly, which was in the same year. So we discussed Brzozowski's algorithm, and we came up with this butterfly. Then it stayed for a while where it was, and then only recently it got published. So we got back to it somehow, and that's then what I will talk about further today. But first, there's one picture. Unfortunately, it's not of you. You've seen many pictures of yourself, but this is not one of them. This is not Prakash. It's a movie. It's called Bellas Mariposas. It's a terribly sad story. about two girls, which are the beautiful butterflies of the movie, living in Sardinia, where they use the Spanish word for butterfly as well, but it's my present. And I want to give that to you as a present. So it's a present by association, if you like. There you go.
Thank you very much.
Thank you very much for everything. I have to admit that this is a European version. I couldn't find an American one or a Canadian one, so probably you'll have to watch it during one of your stays here. This then is the subject of the talk. This is the coalgebra duality for automata. This is also what I talked about at MFPS. I will come to that, and there was some kind of the punchline was missing, and we have in the meantime kind of added the punchline, and I hope you'll appreciate it when it comes. So this is an automaton. This is transition structure, initial state, accepting states. And the duality comes from the fact that this guy in the middle, without initial state or colorings, the transition structure as such, is both algebra and coalgebra. Written like this, it's a coalgebra, and if you move this here, x times a into x, then you have an algebra, so the thing is both. And if you add only initial state, then it's purely algebraic. If you add colors, accepting states, then it's purely coalgebraic. And if you have both x and c, then this transition structure is neither algebraic nor algebra. This is an initial algebra, all words. Transitions are given by a word with an input letter to the word followed by that input letter, so W with an A goes to WA. So that's an initial algebra. This is all languages, which is a fine coalgebra, and with kind of the natural transition structure. And for any choice of x, you get a unique homomorphism into the automaton, which is called the reachability map, and it maps the word W to the initial state x, and then reaching the state on input W. So this is the state reached from x by inputting W. Similarly, by finality here, you get for any choice of coloring, that is to say for any assignment of accepting states, you get what is called observability mapping, and it maps the state x to the language, state y to the language it accepts. All words which bring you to a state which have color 1. Okay, so that's the global picture. This is what I presented at MFPS last year, so I will briefly summarize that again. This is about equations and a canonical automaton representing equations and coequations, and the canonical automaton representing coequations. And because of lack of time, I will just give an example about equations. Consider this automaton, two states and transitions with a's and b's. Then it satisfies, for instance, this equation. The state x, sorry, this state x satisfies this equation. If you take a b, it's the same as staying where you are. And if you take an a and a b, it's again the same as staying where you are. And if you take an A and yet another A, that's the same as doing one A. So you reach, in all those situations, you reach the same state. And coequations essentially are behaviors or languages. So the same automaton again, but now I've colored this state x, double circle here, as a final state. And then the language accepted by x, believe me, is A star, B star. And if I take an A step here, then the language of this y is this language. So the behavior of the state x there, and also, sorry, the behavior of both x and y are languages which are contained in this set. And so that's coequations. So returning to this diagram, in the end, equations will correspond to quotients of A star, and coequations will correspond to sub-automata of 2 to the power A star. But that's already kind of a duality. Same slide, yes. And then for equations, we have this construction of a free automaton, which is a surjection, which is a quotient of A star, and this quotient is exactly with respect to the largest set of equations satisfied by the original automaton. The construction is as follows: you take an arbitrary automaton x, you take the product of x times, so for any choice of initial element you take the copy of x, you take x to the power x if you like, but rather power product of x, and then you take the image under the reachability map. You get a new automaton, and that's what we call free of x. And in this example, this is how it works. So this is the same automaton again, and what you do is you take the product of the automaton, so you have pairs of states, and you take element-wise transitions. And that gives that, this transition structure, and then you take the reachable part from this initial state, and you end up with this guy. And that's what we call free of x. And it has the property that it satisfies all these three states, satisfy all the equations that are satisfied by all of the states of the original automaton. And then, that's another way of putting it, so free of x is the quotient of A star with respect to these equations. Dually, we have co-free of x alpha, and that's going to be the automaton which represents the smallest set of coequations satisfied by x, which is to say the smallest set of behaviors that can be assigned to the original automaton x. And the definition is dual somehow. Sigma of x here is you take the co-product of the original automaton as many times as there are colorings. So this is several copies of x, where for every copy you take different colorings. And an example will make it very clear. Same automaton again, and you just look at all possible colorings of this automaton. So here nothing is colored. Here is one state colored, here is another state colored, and here both of them are colored. So you take the sum, the co-product of those four automata, you just put them next to one another. And then you take the image under the behavior functor, the observability functor. The observation map. So in other words, you take for each state, you look at the language it accepts under these various colorings, and you get these 6 languages. So that's what you get as coequations. This is the smallest set of behaviors, coequations that are satisfied by this automaton. And then we were kind of reaching this point. That was kind of our MFPS, and the story there ended. We knew that this free construction here is isomorphic to what is known in algebraic language theory as a transition monoid. That's defined as a function space. Here we define it as a product in order to be able to define this guy here as a sum. So we had this guy which is very well known, transition monoid. This is kind of a dual to it. It's not known in automata theory, so it's a new construction, and we didn't completely understand its structure. We still do not really. But since this is a transition monoid, this was kind of calling out for a duality theory, or if you like, for Eilenberg's variety theory, and we didn't have it. But then now we made some progress over the last couple of months, and this is what happens. You take this automaton, an arbitrary automaton, you take its free version, so you take the product of this automaton with itself as many times as there are elements in X, and then the image under the reachability map. So you take free, and then if you map that guy under the construction of co-free, so you take the co-free not of X but you take the co-free not of X but of free of X, you get co-free of free of X. Then you have essentially reached then you have found your dual equivalence, because now this guy corresponds to this guy. If I map this guy back under free, it will be the same thing again. So you will get back to free. And this is what we made more precise. So there are 2 categories involved, which is the category of all congruence quotients, A star / C for a congruence relation C on A star. A congruence relation is a set of words with the property that for all related words and for any A, if V and W are related, then also V, A, W, A are related, but also A, V and A, W are related. So it's 2-sided congruence. And you take the collection, the category if you like, of all congruence quotients, which are corresponding to these guys. So as I mentioned, this is the quotient of A star, and as it turns out, the kernel here is a congruence. So this is a congruence quotient. And then on the other side, you take, as it turns out, varieties of languages. So these are sets of languages, subsets of 2 to the power a star, which are complete atomic with subalgebras of 2 to the power a star, which are closed under left and right derivatives. And you take all such varieties with set inclusion. Here you took all congruence quotients with epimorphisms as arrows. You take simply inclusions as arrows. And then this is the theorem. So if you take any automaton which is a congruence quotient of a star, so you have a star slash c, for instance 3 of x alpha, and you map it under co-free to the right, you end up in a variety of languages. And if you take any such variety and you map it to the left under free, you end up again with a congruence quotient. So it was there all the time, but you have to kind of see it. And if once you see it, this is all elementary exercise. This you can give to a student free. This is an example. So this was you remember our automaton, which was more or less this guy over here. Then we took the free version of it. So this is a congruence quotient, if you like. If you now take co-free, sorry, first you observe that this being a congruence quotient is actually consisting of languages as states. So we have 3 states and they are languages. They are equivalence classes of a star after all. So this is 3 of x alpha, a congruence quotient. If I now take co-free of 3, you get this automaton, which is different from the one we saw earlier. Previously we saw the co-free of x, which had only 6 elements. This is the co-free of the bigger automaton 3x, and this has 8 elements. And it's important to observe that, that you have to believe now for me, but these 3 languages, 1, I, and j, are also present here. It's 1, I, and j, plus 5 others. And now you can look at this guy as an automaton, but you can also look at it as a set of languages with language inclusion, and then you get this Boolean algebra, which is finite and hence definitely atomic. And so this is the structure you find always when you take the co-free of something free, or in other words, when you take the co-free of a congruence quotient. And this is then the example summarized. So you take this guy, maps on the co-free there. If you take now from this guy the free version, you end up with the same automaton, which is somewhat surprising because the construction was taking the product. If you take the free of something, you take the product of the thing with itself. So this right-hand side there has 8 elements. So you would expect for the free version of this, a to the 8 elements somehow. But in the end, they all reduce to just these 3. And if you then look carefully at what happens, and there's no time to explain that, but once again it's really elementary, then you find that what this guy consists of, the co-free of this automaton on the left, is really just essentially the power set of what you have here. So all these languages here are just combinations of these 3. So you find 2 to the power of 3 elements, which is 8. Or in other words, you just find back this duality. The classic duality between sets and complete atomic Boolean algebras. So that should make you happy. It's a duality. And you like it. Having arrows gives then the full picture, so quotients are being mapped to inclusions on the other side. And that's essentially it. So there's related work which uses stone duality, which is somewhat more fancy because our duality is really kind of elementary and discrete. But here the situation is restricted. This is work by, amongst others, Mai Dirke and Joanne Krank. There you find a similar relationship, but only for finite automata and regular languages somehow. And if you restrict our situation to finite automata and regular languages, you find essentially the same duality. There coincides. How many minutes have I left?
5.
That's 6. Just fine, thank you. Just to show that we have also non-regular languages, this is an example. I'm going to go through it very quickly, just to give you the flavor. It's we look at the congruence, which is generated by this one equation. So we have an alphabet with 2 letters, A and B, and we want to be able to interchange them. In other words, AB is BA, but not only at the beginning of a word, but everywhere. So we look at the smallest congruence on a star, which is generated by this identity. Then you can quite easily see that this essentially defines commutative languages in the sense that two words will be satisfying this congruence, will be an element of this congruence if they have the same number of A's and B's. In other words, if they are, you can get the one out of the other through a permutation. So we define a language to be commutative as follows. We take this congruence quotient, A star with respect to the congruence generated by this one equation. So this is a congruence. And we take the co-free of that. We know this is a variety of languages, and we call the elements of that variety, we call commutative. Now we know by the duality theorem that a language will be inside this variety, if and only if the automaton generated by the language, or in other words, the smallest automaton accepting L, satisfies these equations. So in other words, in order to prove that the language is commutative, which is to say an element of V, it suffices to show that this automaton satisfies the congruence generated by this equation. And now it turns out that you can benefit from the coalgebraic aspect of the story, which is very much both algebra and coalgebra. But here now we use bisimulations, or rather a variation on the notion of bisimulation. Take a fixed congruence C and call a relation R on languages now in this example. Call it a C bisimulation if the following holds. If any two pairs, for any pair in R, KL, we ask that epsilon, the empty word, is in the one language, even only if it is in the other. And second, for every pair VW in the congruence, we ask that the V derivative of the left-hand side, K, comma, the W derivative of L should be related by R again. So this generalizes ordinary bisimulation because we ask the derivation with respect to V on the left and with respect to W on the right, instead of A, the letter A on the left and the letter A on the right. So this is taking the equations of C into account. And then it's fairly straightforward to prove that if R is such a C bisimulation, or if you like an equational bisimulation with respect to C, and if K and L are related by such a C bisimulation, then first of all they are the same, which is just a classical reduction if you like. But moreover, any K or L for that matter satisfies the equations. So in other words, in order to prove that the automaton K generated by K satisfies such a congruence, it suffices to find the C bisimulation. For instance, look at this language K. It's given by a regular expression. It's not immediately obvious that it is commutative. It is, and in order to show that, we look at the automaton of K, so we look at this automaton, and we show that it is satisfying this equation by constructing a bisimulation, the C bisimulation. This is the automaton. Okay, and then derivatives you get in all four states. For languages, there they are. And now it's completely straightforward to build this relation. You start with KK, you take V and W derivatives of KK, you end up with this relation. So everything here is related to MNO. It's straightforward to show that this is a ABBA bisimulation, and hence this automaton, in particular K, satisfies ABBA, and hence K is. That's about it. So, going back to the diagram somewhere. So this was the extended butterfly. It's no longer a very pretty butterfly. It's getting kind of big. And now it was this duality was really hidden all the time over there. So once you start from something this shape and you throw it back and forth, you have an isomorphism, or more precisely, dual equivalence. There are various questions now to be studied. The expressiveness of quotients of A star with respect to the congruence is rather limited. There's not that much varieties you can define, so you want to try and generalize that. So you will be entering possibly the world of pro-finite constructions, which is also what Dirk and Jean-Luc have been doing recently. And here we probably want to try and do that via these congruence quotients. We want to look at pro-finite extensions of these quotients and see, for instance, if you can reach characterizations of the class of all regular language as a structure as a whole, not one single regular language, but all That's one direction. The other direction is this is all for one particular algebra for automata, and as we have in our Brzozowski paper, we have generalizations for other type of automata such as medium more and was yes more automata really
Weighted.
and weighted and weighted probabilistic automata. So those kind of generalizations might be worth looking at here as well. That's it. Thank you. It has been a pleasure preparing this for you, but I just want to emphasize that much of the thanks should also go to Frank van Breugel. He has really been the main force behind this, and I'm very grateful for him.
Listen to Prakash's real question. Is the real one?
That's my name, 1988, or?
No, absolutely not. I just hope you've learned everything from then. So I was beginning an investigation along with Tobias Fritz on the following program, which was to say, take any duality and try and lift it to a duality between the corresponding automata. And is this what you have done here? Is this program generalizable to any situation, like instead of stone duality, can I just insert Gelfand duality there?
Would be nice. Would be nice. At least it might be an example of that situation. I'm not sure to what extent these constructions of free and co-free will generalize. Because here we're having a very special situation of a structure which is both algebraic and co-algebraic. We have a very special role for the initial algebra, the corresponding functor, and final co-algebra. So, but as a program, yes, I think it's it makes much sense, and this is kind of, I think, fits into the same view. Yes.
More questions? Okay, then we're right in time for the next. Let's speaker again.